Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today we're very happy to have Tariq visiting us. Tariq is a PhD student at Colorado State University, and he's worked on searchable encryption and ORAM, and today he's going to talk about particularly recent work in ORAM.
Thank you, Melissa, for the introduction. Hi, everybody. So today we will present two ideas on Oblivious RAM. The title of my presentation is Towards Practical Oblivious RAM, is to make Oblivious RAM more practical. You can understand that we are enhancing the search complexity in our work. We will also talk today in our agenda about another aspect of Oblivious RAM, which is how to make Oblivious RAM resizable. Because nowadays you can know that Oblivious RAM, when it's created for a fixed data set, fixed number of blocks. And I think that as far as we know, it was like the first idea how to make ORAM resizable, depending on the needs of the user. If he wants, for example, to increase the number of elements or decrease the number of elements, how to make it, adjustable. And this problematic is only for tree-based ORAMs that we will talk about later on. So I will begin by just giving you like a very high-level idea of what is Oblivious RAM. Particularly, so when a user stores his encrypted data, just imagine the encrypted data are blocks in the server, okay? So when a user accesses one block, these blocks are encrypted, of course. So he will retrieve this block, the intended block. So between these, any successive accesses, you can imagine that the data is shuffled. Some of the schemes shuffle totally, and some of them shuffle partially. And the more efficient are those that they can shuffle partially, and they are called tree-based ORAM, hierarchical ORAM. So they are shuffling the data partially. So whenever the user accesses another time, even the same block, he will access another place in memory, basically. And it will be encrypted differently, so he will not know, the adversary here, he will not know if the user is accessing the same data or different data. So this is why we call Oblivious RAM is hiding the content as well as the search and access pattern, because the search are not correlated and the access pattern as well. So this is the high idea of Oblivious RAM. So to get more in specifics, so one of the more efficient Oblivious RAM actually in literature are those called tree-based ORAM. When you imagine the data structure is constructed as a binary tree. So, and these blocks are here in the nodes of the tree. So imagine that we have our binary tree. So if you want to store n elements, let's say n elements, you should create a binary tree of n leaves. So every bucket or node is composed of blocks. Okay, these blocks are the data, actually, what you are storing in your memory. And so you can see that we have a lot of blocks, but we have very small number of elements. This will be for security purposes. When you are accessing, you should be always oblivious between two different accesses. So as a normal memory access, we have always the read and the write operations. We should have these normal operations. And we have talked at the beginning about shuffling the memory. So in tree-based ORAM, it will be a little bit different, what we call an eviction process. And I will explain it more into details in the subsequent slide. And so this is from the one hand. From the other hand, we have two types of ORAMs. Even in the tree-based ORAM, we have what we call constant client memory ORAM, and there is also polylogarithmic client memory ORAM. So what's the difference? So the difference is, as the name shows, is the client will not store basically anything in the first type. It will be constant. And this will be very good for, scenarios when you have smartphones or something that doesn't have a lot of memory. For the second type is polylogarithmic, when we allow to the client to have a polylogarithmic number of blocks in the memory. So what are the consequences of these two types of structures? The first one is it will allow per access search communication complexity, which is a log cube in the number of elements, where the blocks are at least log n. Okay? The second is more efficient. You can see that we can perform a log n per access. But you can see that there is a trick here in the parameterization where the blocks should be at least log square n. So basically, if you take both of them into consideration, there is like a factor of log n, which is in the difference. And the stash, which is the memory here of the client that we should store, it will be a logarithmic in n, which is quite good in some scenarios.
This is all like the number of bits you have to store for each.
So basically, this is in bits, and this search communication complexity is in blocks. So you should multiply to have like the correct number of bits. It will be log 4 to the power of 4n, which is huge if you are taking like some size of block like 64, 512 or something. It will be like, so you can just see this communication complexity like a multiplicative factor. Basically, to download like 512 bits, you should have log to the power 4 and multiplicative factor to download, I mean, log to the cube and multiplicative factor to download the same block. You can see it like as multiplicative factor. Yeah, go.
Actually, if you're talking about like path or things, it's order log n number of blocks, not bandwidth, but just the size.
Yeah, exactly. Yeah.
You need to download and upload order log square n blocks.
Yeah. And here you can see that there is a big O notations here. We are hiding, for example, the access to the position map that I will talk about now, and also the number. There is an upload, there is a download, there is like a multiplicative factor of 2, that it's not negligible at some point when you want to download like 10 megabytes and at the end you will download like 20 megabytes. It's a huge difference. Just it's a multiplicative factor of 2, but it takes bandwidth actually. So I will finish now how we construct these tree-based ORAMs. So for each element, you can see that in our tree we have 4 real elements for 4 leaves. We should associate every element to a tag, which is the leaf number. So for example, element 2 is associated to leaf 1, leaf 2 is associated to element 1, etc., etc. So basically, if we are going to store this position map in the client side, it will take n log n bits, okay? Which is not what we want to have, actually. We want to have a constant client memory. If we are going to store this position map in the client side, it will annihilate this advantage. So the trick that it was proposed by LNG paper here, because this scheme was proposed by LNG and colleagues in 2011. So what they are doing is they are storing this position map recursively. They are creating like small ORAMs that they have a number of leaves which increase exponentially every time. So we have like 2 leaves, 4 leaves, etc., etc. And at the end, we will access the associated leaf. So basically, in this log cube, and there is a logarithmic number of access to the Oblivious RAM. And this will also make the ORAM, which is a little bit, needs a lot of communication complexity as well. So you can see. So, tree-based ORAMs are one of the best because it was the first one who is introducing the worst case, which is polylogarithmic in the number of elements. Because before, if you want to shuffle the memory, you should shuffle the entire disk, which is linear and it will cost a lot. So here, every time you are accessing, you are introducing an eviction step. And this eviction step, which makes actually the access polylogarithmic every time. So this is like a huge advantage in ORAM. And lots of schemes actually that they are appearing in the literature right now, they are based on tree-based ORAM. They are modifying, for example, the eviction process. They are modifying, for example, the structure, as we are going to see in the scheme that I will present today, just to make this logarithmic a little bit smaller by multiplying by a coefficient, constant factors, etc., etc. So as I mentioned here, the challenge is to enhance the search complexity. So I will give you just an idea how a read, in general, an access works. So just imagine for the time being that our position map is stored on the client side. And the client wants to access the element 1. Okay? So he will go and check the position map, and he will find out that leaf 2 is associated to element 1. So he will send to the server, give me all the blocks that they are in the path starting from the root and going to leaf number 2. So it's 100 probability, 100% sure that the element will be there, okay? So he will download the entire path. Here you can see that this log n come from, first log n come from. And in LNG paper, the number of blocks per each node, it should be log n. So we have this log square. And there is, at the end, there is this position map axis, which is actually multiplying by log n, which is log cube. So this is why the log cube came from. So let's assume that the user, the client will read this path. He will read all the path to stay oblivious. He will delete this element from this bucket, read it or update it or write on it something else. He will always put it on the root on the next step. So when you put an element on the root, you cannot just let the element stay there forever. Otherwise, the bucket will overflow. So if you are reading like a lot of elements and put always the element in the root, at some point it will overflow. So you should introduce this eviction process, which basically will percolate elements toward the leaf. So what the eviction, like there are a lot of evictions algorithm actually in the state of the art. So the one which is presented by LNG, how it works, basically you are taking like an eviction rate which is like, let's say 2 elements per every level. And you are taking these real elements and percolating them towards the leaf by reading and writing again, etc., etc. And there is a security proof that it will never overflow with a given like probability, which is based on the size of the bucket. So this is why you should really fix the size of the bucket in some way that will not overflow. So for example, here we have our element, and when we apply the eviction, it will percolate toward the leaf which is associated to. For example, leaf 1, it will always go, to the exact leaf. But to stay oblivious, you should always write on the left and the right child every time you are accessing a node. So the adversary will not know which leaf actually is associated to. And since the eviction are random, you are selecting randomly the nodes in every level, he will not check. He will not know which leaf is associated to that element. And so basically, every axis is associated to an eviction. So eviction is just plus, so it will not modify the O notation, okay? So as I have said, this position map is stored recursively, which means we have like, to access the main ORAM, which actually stores our data, there are a lot of more small ORAMs before, which called the position map. So in our construction, which is done with while I was in Northeastern University with Eric Oliver Blas and Guevara Nubir, is how to decrease the search complexity, how to make it a little bit better. So we know at the first hand that it's so difficult to reduce a logarithmic complexity. So we thought about how to make this logarithmic a little bit smaller by just multiplying by small factor, which is lower than 1. So our construction will present a tree with different height. So where the average height to access an element will be smaller than log n. So this is like the main idea behind r-ORAM. So the idea seems straightforward, but to make it work and the security proof to be correct, you should make sure that the overflow probability will not increase, for example, the size of the buckets, which boils down you are downloading more, and you are not gaining anything. We should always keep the size of the blocks here. For example, here there are 4. We don't want, like, for example, to reduce the height and increase the number of blocks, so which will make no sense. So how the construction looks like. So just imagine that we have an outer tree, like with say 4 elements here, and we will associate to every node recursively a number of inner trees, where every interior node of this outer tree is a start of another tree, which is inner tree. And at the end, we will have a number of recursion, and at the end, we will have a leaf tree, which actually stores the data. So this is the construction. So we are interested on counting the number of elements, the height of this construction, what is the worst case, the best case of access, etc., etc. Because you can see we can have a tree here, which is starting from the first level here, and there is another tree which is starting at the second level. You can see that there are a lot of paths that they are actually having like best case, worst case. And we are interested also in computing the worst case. Keep in mind we have the recursion factor R. We have R-1 inner tree, all of them, outer and inner tree, they have a number of nodes which is y, and the leaf tree has a number of elements which is 2. So some features of our r-ORAM. So the number of elements of these constructions follow this relation to the power r x y minus 1 to the power r. So contrary to the construction of normal binary tree, full binary tree, all the number of elements should be like 2 to the power something. So here we have a little bit different number of n that should be verified like this. Yeah.
Minus what x and y and r were.
So yeah, so x is the number of nodes in the leaf tree, and y is the number of nodes in, I mean, not number of nodes, sorry, number of leaves. So here, for example, we have y equal to 4, y equal to 4, and here x equal to 2. So the number of elements, if you count all the number of elements, which basically are stored in the leaf tree, they will verify this relation. So you can see it like we have here. How many nodes do we have? We have 2y minus 2. Okay? Because it's full binary tree. And 2y minus 2, we are multiplying every node with 2y minus 2, 2y minus 2, r times. And at the end, we are multiplying by x. So 2r xy minus 1 to the power r. So the number of nodes, we can compute it like this. So just to give you an idea, so these number of nodes are like 20% less than a full binary tree, where we are storing the same number of elements. Let's say that we are fixing the same number of elements n, okay? So with the full binary tree, we are storing like 2n minus 1 node, okay? In a full binary tree. Here, if you take the appropriate number of nodes, that actually we will optimize on y and x, okay? If we take the appropriate number of y and x, at the end, we will have like a 20% storage better, which is, in a practical view, it's an enhancement, because we want to reduce. Since it's logarithmic, in some sense, it's very hard to do better. The access. So we should decrease this constant as far as we can. So the number of nodes, we will reduce them. And we will see later on in the security proof that our security, the overflow probability in this scheme is better. What does it mean is the number of blocks, we can reduce it as well. So we will save storage in 2 aspects. The first aspect is we are reducing the number of nodes, and also we will reduce the number of blocks per node. So
what's this number of nodes shows? Because in path ORAM, what they do is they need to store 20 n number of nodes. And when they can only store n number of nodes, so there is an overhead of 20.
So if you are counting the position map as well.
Yeah, everything.
Yeah. No, here, just keep in mind, it's just the main ORAM, okay? We have in the paper, if you are interested to read like the accurate number, we are still saving like 20%. So the path height, which is like the most interesting thing. So the path height means what is the communication complexity to access an element. Since we have different level of nodes, of leaves, we will have different communication complexity depending on where the element is. So the worst case is r log y plus log x. So I will come back for you to understand why we have this worst case. The worst case is when you are starting from the root and going till the last level of every inner or outer tree. So when we have y leaves, we have log y, etc. r times r log y, and x at the end, which is log x. And the best case is when you are accessing in every recursion just the first level, which is r times plus log x. Okay? So honestly speaking, having these, we can make them smaller than log n, okay? But we are not interested only on the worst case and on the best case. We are interested on the average case. What's the average access? Because it's the one that will show us if we are saving a lot or nothing. If our average is near the worst case, basically we are not saving that much. So we want to make the average cost also very small. So this is our optimization problem, actually. It's based on optimizing the average cost. So yeah, so here it will give you an idea about the entire structure. Here you can see that structure is here, but if we put everything in two dimensions, you can see that we have the recursion here, we have the second recursion, which is starting here, and you can have like different level of leaves. This is, you can picture the distribution of leaves, actually. You have this level, the second level, the third level. You can see somehow that when the tree is getting bigger, more leaves will be in the middle. And I will show you the distribution, actually. It's normal, exactly normal distribution. Okay? Our construction is a normal distribution. Where the mean, the average and the median are the same. So, I don't know where this comes from, but so we are interested also in a recursive ORAM. We should also be interested on the position map, how to access an element. In a binary tree is simple. When you are starting from the tree, there is like 0, 1, 0, 1 from the left and the right child, and you can go easily to the leaf that you want to access. But here, it's different, because we have sometimes 4 children, and sometimes we have like 2 children. We should make sure that we are mapping exactly. So basically, we can map just by getting, for example, if we are in the same tree, we will give 0, 0, 1, 1. If we are going to another recursion, we will give like different bits. And the size of our map, when in path ORAM, LNG ORAM, gentry ORAM, etc., all of them are in log n, because they are n element, log n is sufficient to map any leaf. But here, since when we are using sometimes 2 bits, our map should be between log x, which is like the best case, and 2r log y plus log x. In general, just keep in mind that our map is lower than 2 log n to map our leaves. So we have done our optimization problem, and we came up with these results. So if we choose our recursion factor log n over 2 to the power 1 over 2.7 and x to 2, the worst case is 0.78 log n, okay? And the best case is 0.4 log n. So these factors are so important in terms of communication complexity, because when you are communicating with your ORAM, you are paying money, right? The bandwidth and the number of gets and put, depending on which database you are storing your elements. So reducing by, like instead of paying for log n, you are paying for 0.4, is like reducing by 0.4 the cost that you are paying per each access. So, but as I have said, these values are not saying that much about the complexity of our structure. We should consider the average cost. So the average cost, we are taking that, like verifying this relation where so Ni is basically the number of leaves that you have in every level, in the ith level. And we are multiplying by I, like a weighting factor, and dividing by n. So we want to know what this combinatorial formula looks like. So we have 2 graphs here. The first one is a normal approximation, and the second one is we have just taken this binatorial and put it in MATLAB, and we have like found exactly. We didn't do any approximation here, so it's exactly nearly the same. So basically what it means that the number of leaves, the distribution toward in the height, they are normal. So in the middle we will have lots of elements, and at the end we will have smaller. Yeah.
If you rescale the normal distribution, it could be made to fit the empirical curve much better.
Yeah.
Looks like your standard deviation is too low.
Okay.
Jack it up a little bit, and the roof will come down, and the tent side will come up, and you won't be able to see the difference.
Yeah.
So why did you choose this particular?
So when I have just put the normal distribution, you should fix these parameters, and these parameters are based on the number of leaves. It's like the modelization that we have done is like the number. It's like balls and beans paradigm, and we are just counting. It's a counting problem. So yeah, maybe it will fit better. But at the end, we have like very similar. You can see that here we have like for the level which is like around 19 is like instead of having the exact distribution is around 850 and the normal is 90 is around. Leaves here. So this is a theoretical evaluation, actually. We have taken 3 different Oblivious RAMs. We have taken She et al. And colleagues ORAM, Path ORAM, which is one of the most efficient in polylogarithmic ORAMs, and we have taken Gentry with the branching factor, which is K. We have another branching factor because their scheme is working with a K-array tree and not a binary tree. So our scheme, you can see it as a plugin. So our plugin, it can fit with any tree-based ORAM, and we can optimize the height. You can see it like that. You can put it in any ORAM with its own eviction process, and we can save the height. Because our contribution here is how to save the height in the height. And the height is like the main factor in the ORAM. The factors are the block size and also the height. So if you are saving one, it's good. So you can see that we applied our path or our R or recursive ORAM on different structure. So here we have applied to SHE-AR. You can see that the communication is in megabyte and per axis. So here, if you want to access and you can see that this is a logarithmic scale. So we are doing every time better. So because it's straightforward, we are enhancing the height, which has like a direct repercussion on the communication complexity. So in Gentry AR and everything, we are doing better.
So this is because you have small ORAM for small data sets and big ORAM for big data sets?
So here, your question is the data size?
Yeah, that your ORAM becomes bigger?
I mean, it's the number of elements. We are fixing the block size, right? We are fixing the block size. Let's say I remember that we have taken 1024 bytes. And this data means that you are dividing the total number of data on blocks. You see what I mean?
Yeah, but I mean, where is this gain coming from?
I mean, from the height. So if
your height is small here, right?
I mean, it's the same.
Height increases with the size of the data.
I mean, logarithmically. When you have, it's log n, right? When you have, I mean, n, which is bigger, our enhancement is like constant. It's 0. In the average, it's around 0.65 or 68 in the average. So we are saving like 30%, 30 to 35%. So this is why we have like this basically the same difference between the both ORAMs. Here, your question why it's smaller, because the tree is flatter, because you are using a branching factor which is like enhancing the dimension of the tree. So the height, even if we optimize the height, it will be small. Yeah.
Are the numbers theory, or did you find a real 1 petabyte database?
So this is just a theory.
Okay, sorry.
No, I will have an experimental graphs as well. This is like the theory, and I will present that our work is also experimental. It's not just in theory. Yeah.
So this is average case communication, which
Yeah.
is what really
It's
because everything's random accesses.
Yeah, random access. It's like it's based on, I mean, you will see in the experimental phase, we have taken 2 to the power 50 random access to find out the average.
So the r-ORAM is just like binary tree.
Yeah, it's binary tree.
Yeah, so why not, if you do it like the same way that you are doing, you make it flat?
I mean, you want to make the path ORAM with the branching factor more than 2.
Yeah.
So I mean, in the security, it will not work. In the security proof, the eviction that they are using is different from the one that I have explained.
But the construction will work, but you need a different proof.
Yeah. Actually, you will see the results of our proof. But the problem, I mean, why we don't have any path ORAM, maybe as far as I know, that it doesn't have a branching factor more than 2. It's because the security proof will not work. And it's not it will not work, but the size, the Z that I will say the Z, because the path ORAM has a constant block size. It's like 5. Okay, 5, they say that it's not proven, but 4 is also good. But if you are taking like a branching factor, which is huge, the size of the block will increase. So at the end, you are not gaining in communication complexity, right? Because you are downloading more blocks. So, I mean, so here you can see it's a communication in megabytes. But if you are taking in terms of dollars, and this is like it was the evaluation based on Dynamo S3, they are including not only the communication, they are including the number of get and put. So if you are decreasing the number of blocks, it will be better also, even if you have a block size which is larger. In terms of communication, as the pricing that they have set in Amazon, for example, it's cheap for the communication in bits. But when it gets to put and get, it's a little bit, I mean, expensive. I mean, depending on the number of blocks that you are accessing. If you take also that in consideration, it buys a little bit the results. If you can see. Actually, Gentry, because it has like a branching factor which is huge, you can imagine that the block size is smaller, the number of blocks that you are accessing, because the tree is flat. So even if you are downloading more bits in communication complexity, the number of put and gets is smaller, which makes it like sometimes like path ORAM. But as I have said, this is like a result for a fixed constant block. We didn't investigate more about if we increase the block size or decrease the block size. Of course, it will have like a repercussion, but it's for fixed block size. So we have two, I will show only two theorems about the block size, because ORAM, the main security proofs will be on the overflow probability of the bucket, right? So you want to prove that during an access and when you are eviction, you will not have somehow a bucket that will overflow. Overflow means that you have more real elements than its capacity. For example, for path ORAM, if you have path ORAM, because they have stash, maybe it's a wrong example, but if you have a LNC and colleagues path ORAM, it will be, you have log n. And if you evict like log n plus 1, it will overflow. And the server will know it's an error of correctness of the scheme, and he will know that there is a mistake. This bucket contains like log n, exactly log n real elements, and this security breach. So the security proofs on ORAM focus more specifically on this overflow probability. They want to make it like very small depending on the block size. So for Xi and colleagues, when we are applying our recursive ORAM on Xi and colleagues, we came up with, if you fix the probability of overflow to, let's say, omega, which is very small compared to 1, your block size should verify this relation, log n over omega, okay? And this is like the interesting result that we have. Surprisingly, we are reducing, actually, the block size for levels that they are more than r. If we came back to this structure, there is like, the levels are from r log y here, r log y plus log x. If the number of level if the level is larger than r, the block size, we can just set it to this value. And we are gaining I minus r plus 1 every time. Every time we are going deeper, we are like decreasing the size of our blocks, which is a huge impact on the storage complexity and also in the communication complexity, because we are reducing also the number of blocks. It's not only the height, but also the number of blocks. So we have also investigated applying recursive ORAM over path ORAM. And here it's a different story. Why? Because we are not taking into account the size of the blocks, because they are fixed. So we don't want in that scenario that the stash, which is the memory in the client side, to overflow, because you have fixed overflow, you have a fixed polylogarithmic memory. If you are evicting, you don't want to have like some elements which go beyond this stash. And this is the overflow probability that we should make sure that it's very small. So with path ORAM, we make that the size of the stash is also logarithmic in the probability that you are setting, which is like the same result that they have in path ORAM. But the problem in our solution, we are not doing as good as them in the stash size. Our stash, as we are going to see in the experimental phase, we have sometimes up to 10 blocks more in the stash. We are not doing as good as them, but it's not the only blocks that we are pushing in the stash, because when you are eviction in path ORAM, you are downloading the entire path, right? And the entire path is log n times z, the number of blocks that you are putting also in the stash. So the correct number of blocks in the stash will be r plus this path that you are downloading. Since our path is much smaller, this addition in our case is much smaller than their case. So basically, our ORAM, the memory size that we should, allocate to recursive ORAM is much smaller in general than path ORAM. I will come back to this later on. So we have done some experiments. We have implemented recursive ORAM on path ORAM. So we have a comparison here between the height. So here, basically, this is like a binary height, and this is the average height that we have after 2 to the power 15 random access. So we are gaining, in general, 30 to 35% over the height of normal binary tree, full binary tree. So this is the average height. So basically, this is the average. The worst case will be something which is also smaller, but between the graphs. Because if you remember, we have 0.78 log n, which is around 20% gain. Sorry. So we have taken different block sizes for path ORAM and r-ORAM. And you can see that r-ORAM outperforms this. I mean, again, this communication took into account the position map. It's not just the main ORAM. It's take all the communication, eviction, upload, download, everything. So, and you can see that it follows like the same shape of the height, because what we are modifying is the height. So path r-ORAM, in both cases, 5 and 6 block sizes are better than both path ORAM in the same block size. So we are doing better in terms of communication complexity. And here, those are the results for different block sizes. You can see that here is 2017, 2018. And if you are increasing the number of elements with the fixed block size, you are increasing the data size. So here, basically, we have taken 4,096 bytes. That if you multiply by 10 to the power 7 is like around like 40, like 4 tera or something around, yeah.
Could you give me I'm having trouble understanding the intuition for why the recursive structure has this effect.
I mean, this is a good question actually, how we came with this structure, why we are saying that it's better. So our motivation was at that moment when we wanted to decrease the communication complexity, we said that the main problem actually is that all the leaves are in the same level in the binary tree. So always when you are accessing the whatever element, you are going always log n. We said that somehow it will be better if we put elements in different levels. So our first, technique that we thought about is just check the full binary tree and consider every node, interior node, as a leaf. So if you as a leaf, and when you are accessing, you will accessing, for example, a path which is 1, 2, 3, etc., which is like increasing exponentially. But our result shows that you are not gaining that much, because the average height in that case will be, instead, if you have a height which is L, the average height will be L minus 1, which is log n minus 1, which is not that good. So we have thought about how we can distribute following this, this normal distribution, how we can have this curve.
But it seems like having a bunch of nodes in lower levels means you have to have more at deeper levels. Why does it?
No, not necessarily. Why? Because the trees end at the given time. It will not go.
But you have a certain number of real blocks you have to store, and so if some of them are at smaller levels than average, some of them have to be at bigger levels than average, and it feels like there should be more in there's just more tree there going down to the deeper levels. So it feels like there should be more nodes at deeper levels.
Yeah. So no, you're right. So basically, so the graph that I have shown here, it's not exactly the level, the 19 level, because you can see that we have divided on 2 to the power I. So 2 to the power I is the number of leaves that they are branching, actually, when you are getting further. So basically, I didn't put the figures, but basically, when you are multiplying by 2 to the power I to have the exact number of leaves per level, it will be biased towards the deepest level. Yeah. So this is why the average is just 30%. This is why. Because in that case, if we just take this curve, you can see, okay, why it's not 50%? This is your question, why it's not 50% with this curve? But actually, you should multiply by 2 to the power I, so the curves will be biased toward the deepest level.
Isn't that bad? Because the deeper the level, the more communication cost you have.
So we are still better than the normal binary tree, because we are downloading a path which with the height which is lower than log n, right?
But for some cases it will be bigger, right? Because that's
why?
What you're doing. Because some heights are smaller and some are bigger.
No, you didn't get my point. So even if it's bigger, the worst case, it's still lower than log n.
Yeah, why? Where did the magic come from?
So let me. So this is like kind of magic, exactly. So you can see here. So this is a picture that can a little bit. You can see why. So it's small tree, right? But you can see that at some point the recursion ends, because you can go further r times. Okay. When the recursion ends, you stop. So these leaves will not be the parents of other leaves. So this will stop. So, and in the middle level, since we have a lot of leaves, they will not continue. So the number of leaves will decrease again. So we have like a normal distribution. This is why we have a normal distribution with this construction. There is another point is it like the best construction that we can have? Because we have optimized on the worst case, not an average case. If we have optimized on the average case, maybe we get a better scheme, actually. But to answer your question, so why it will end? Because we have more leaves. Theoretically, we have proved that we have more leaves in the middle. And what it means to have more leaves in the middle, it means that there will be less leaves because there is no enough parts for creating new leaves at the end. So you will have like this normal distribution.
So if I do exercise for like all n blocks in your scheme and all n blocks in path ORAM, then the combined cost will be same?
No, it will be better in our case. Why? We have a worst case which is better. Okay? The worst case. So one thing to understand clearly, in path ORAM and all full binary tree, the cost, the log n, is at the same time the worst case. Okay? The average case, the best case, is log n, always. Here, we have a best case and worst case. So the best case will be like 0.4 log n. The worst case is 0.78. Okay?
Is that partly because it's not always binary? It's sometimes
Exactly. Yeah. There is like a branching factor there which is hidden, which is like the recursion, because you can see here, there are sometimes like nodes which has.
Okay, sure, but why is that? So, but wouldn't it be better to just have a k-array tree?
This is a very good remark, actually. Why? It will work if you want just to access and you don't care about the overflow probability. But to prove the overflow probability when you have a branching factor which is huge, it will make the block larger. So the blocks here, the nodes, they are storing some blocks. They are like 5 or 6. When you are making the branching factor, like let's say the asymptotic best, it will be log n. But if you have like a log n branching factor, it will be huge. The block size will be huge. So you are not gaining that much. So there is a dilemma between the height, the branching factor, and the overflow probability that should be small for the same. We are aiming for the same block size.
Maybe you need a new proof technique, right? I mean, that's what path ORAM did, right? I mean,
yeah, this is what we are doing actually. So no, we have tried with branching factor, which is huge. I mean, which is like 4, because we can apply this structure with k larger than n, larger than 2. But the problem at some point we are getting like a huge number of blocks, and which means that the communication complexity will be, we are not gaining, we are losing. So there is like this optimization problem as well. So there are a lot of factors that you should take into account. There is your intuition is right in the sense that definitely, if you have a like log n branching factor, the tree will be flat and the height will be good. But the problem in that case, the number of blocks per node will be huge as well.
I guess I'm looking for an intuition to explain why having a broader branching factor in your way produces smaller blocks than doing it in the standard way. And I still don't have that intuition, but maybe we should talk about it.
Yeah, but it's about the security proofs. When you are going to the security proof and you see that this branching factor is playing a huge role in the block size, you should let's say, you are taking an overflow probability is 2 to the power minus 64. You don't want that any bucket will overflow to the power 64. And you are fixing this value. So when you are fixing this value, you should fix the block size. Okay? The block size, I mean the block size, the number of blocks per node. If you are taking a k-array tree with a k which is large, you should have a number of blocks which is huge. And if you are computing again the communication complexity per access, it will not be that good against like path ORAM or something like that. So there is like an optimization problem also depending on the security of your overflow probability. It's not like a height problem. It's not, we are not just trying to optimize the height without looking to the security proof. We should take it into account. Of course, if you are taking a k-array tree, which is like log n, you have like log n over log n, which is like, I mean, the best in terms of height. But the problem is when you are proving with an eviction problem, which is similar to path ORAM, you end up with saying, okay, I'm increasing the number of blocks per node a lot, and I'm not gaining that much. So this is the problem. So these are like the simulation over 512 bytes, 124 and 4096 bytes per block. And you can see that our r-ORAM is much better than path ORAM with the same block size. with the same block size, and we will see it in, in the proof of the stash we have done some experiments on the stash size, because it's very important. Of course, you can come up with path ORAM with the block size which is equal to 1. But what's the repercussion on the stash size? It will be huge. So you cannot store that much block in your client memory. So you should fix this block size in such a way that the stash will not overflow. So to give you an intuition, the behavior of our stash, so the security parameter here mentioned 2 to the power 20 operations. We have done 2 to the power 20 operations. And the stash, you can see it has like a logarithmic shape because these scales are in logarithmic scale. So we have, for example, for z equal to 5, we have 80, which is bad. So our theorem proves just for z equal to 6 and larger. And for z equal to 6, you can see that the worst case, this is the maximum value, which is 40 blocks. And here you can see that it's 90. So you should store 90 if you want to reduce the block, which is not good. Sometimes if you have a block size which is 4 megabytes or 10 megabytes blocks, storing like 100, it will be huge. So this is why you should take into account also the stash size. And also, here are other graphs for z equal to 7, z equal to 8. But here we are also increasing the communication complexity because we are increasing also the block size, which is not good. So the best z for our ORAM is z equal to 6. In path ORAM, it was like 5, 4. So if we are taking into account this honest comparison between both schemes, we are still better. Also when we have like a difference of 2 blocks per accesses. Also the other aspect that I have talked about during the beginning is the stash is not the only factor. Because you have a stash, and also when you want to evict in path ORAM, you should download the entire path. So you should put it also somewhere in the memory. So the size of the path is log n times the block size, plus the stash. So for the same, if we take, for example, z equal to 6 or z equal to 5, even if we have 90, but our height is smaller, when we are downloading and putting everything together, we are better than path ORAM. So if we take everything in consideration, the memory that should be allocated for r-ORAM is better than the memory allocated to path ORAM. So this graph shows the average of our stash because the stash height is very important. So as you see for Z5, we are not controlling that and we don't have any proof for that because we can just prove for Z equal to 6 and larger. So, and for these values, we see that logarithmically we have good shape, which is similar to the shape of path ORAM, but at sometimes 10 blocks more, sometimes at 10 blocks more. Sometimes for path ORAM, for the same security parameter here, for example, 29, it will be like 11, 15, or something like that. So we have seen like an enhancement of the search complexity over tree-based ORAMs. And now we are tackling a different problem, which is how to resize a tree-based ORAM. So our technique is just as the first paper actually, we are just tackling the constant client memory. We are not investigating on polylogarithmic memory how to resize polylogarithmic tree-based ORAMs. So we have only the constant client memory. So what's the motivation of resizable ORAM? And we will see also how we are tightening a little bit, revisiting the first paper of 2011 of LNG by reducing a little bit, tightening the bounds of the block sizes and the leaves, etc., as we are going to see. And we are investigating adding and pruning. So as I have said, existing tree-based ORAM are initialized with a fixed number of blocks. So we should investigate, is it better? Is it straightforward to add a new line of leaves? Is it simple? Why they are not using this technique? For pruning, just deleting a line of a level of trees. Is it simple in constant client memory? So we are investigating those questions, and it seems that they are not. Especially for pruning, it's a huge, it's a problem actually. If you want to deploy an Oblivious RAM on the cloud, you should take both of these scenarios into context, into consideration, because at some point you want to delete something. So you will not pay for the same number of elements that you have initiated your ORAM with. You have at a given time 10 terabytes, and sometimes you have like 5 terabytes. You want to reduce a little bit your storage. So for constant client memory is a little bit tricky. Why? Because at a given time, every access you should have a constant number of blocks in the client side. So if I come back here, I mean that I have maybe, let's see this tree. So in LNG, the paper that we are investigating here, so to download the path, we are not downloading the entire path and putting it in the memory. We are downloading block per block. So to have a constant client memory, we are encrypting again, and see whatever, if the element is there, etc., etc. So it's not like path ORAM when you download the entire path and store it in the memory. In LNG and colleague paper, like they are downloading block per block to have like a constant client memory. So if you have an element and you want to delete it, or you want to delete the entire level, you should check somehow if there is an element there. Knowing that every node is log n, you cannot store the entire log n there. So there is like some problems how to delete, to prune a node while keeping this constant client memory.
So path ORAM is also constant client memory, right? Because they assume this block size of log square n, right? I mean, which means they can do some level of recursions, and then after log n recursion, it is constant client storage.
What do you mean by, no, they have the stash, always the stash, right? Which is logarithmic, okay, in path ORAM. And after that, they are using the trick of least common ancestor that it was presented by Gentry the first time. So if you want to apply the least common ancestor, you should download the entire path. There is no way that you can just download block per block and find the least common ancestor. So they are downloading the entire path, storing it in the stash. So at a given, even if it's volatile, because they need it just at a given time during the access, they have z, which is the number of blocks, log n, which is the high time, log n, plus the stash. So which is not, so what I mean by constant block size, which is like 0 of 1.
But they mentioned in the paper, I mean, that you can get a stateless ORAM by storing the stash in the cloud and downloading it with every block.
They are giving the capability to the server to find the least common ancestor. I didn't read that. Maybe I don't know if they exist, but as I know, if you want to apply the least common ancestor, you should locally decrypt to see. Because, I mean, they can't put the stash, but I think that they are using this trick for multi-party also ORAM computation for everyone to get access to the stash or something like that. But in client memory, they are always polylogarithmic. If you want to apply the least common ancestor, there is no way. So there are some actually other papers that they are trying to optimize how you can find the least common ancestor, etc., etc., especially for circuits when you are applying the circuit on ORAM, like SCORAM or something like that, recent papers. But the problem it's polylogarithmic, and it's different scenario from LNG and colleague, where you are downloading and only one, maybe sometimes 2 blocks, but that's it. It's a constant number of blocks. So even imagine that your blocks are huge, 10 megabytes or something like that. So it makes sense that these kind of ORAMs still have like a good repercussion. So this paper was accepted in Financial Cryptography to appear in 2015. So our question is, what's the best way to add new elements? Is it naive, like adding new level of leaves, or maybe like dynamic, adding like just a leaf when we need an element, or a lazy insertion, etc., etc. We are investigating all these techniques. So when we are investigating this technique, it's not just from a protocol view, it's from the block size. What is the best block size? If we are using this technique, is it better than the other one? So we should investigate all these aspects. So this is a good question, actually. Can we maintain the same overflow probability with the same block size? So this is also a question. If we are increasing the number of elements, for the interior node, are we going to increase the block size or decreasing in it? So this is a question that we should ask yourself when you want to have like a resizable ORAM on the cloud. And also this pruning, since there is no technique actually that can do that, so we are introducing an oblivious pruning technique how you can do it in a constant manner. So, as I have said, the first contribution of this work was tightening the bounds. So we have revisited the first paper of Elenchi and colleagues, and they have introduced that the best rate of eviction was 2, but it's not true. The best rate, it's 4. Why? We have the same communication complexity. Why? Because we have a bucket with half size. Whenever you are downloading the path, you have a block size which is half, and you are the same communication complexity. But we have less storage with an eviction rate which is equal to 4, because you are reducing the block size. And since you have a fixed number of nodes, you are reducing by half just for the interior nodes, the storage, so which is better. So with the bucket size, which is k over log, which is base 2, the eviction rate instead of k. So if we are choosing an eviction rate with 4, we are dividing basically the block size by 2. We have the same probability of overflow for an interior node. So for all interior nodes, we should take into account the entire height, etc., etc., and we have still an overflow probability which decreases exponentially with the size of the blocks that we have fixed. And with the Ball and Beans theorem, I mean, we can also find the same. We have tightened, of course, because it was not described well in the first paper, and we have presented a better overflow probability, which implies that we have better block size, number of blocks. So this is like the first contribution. We have provided better bounds for the block size, which has first an implication on the storage and the communication that you are downloading every time from the ORAM. So at the end, this is quite good, because now it's the eviction, you should fix it to 4 and not 2. So we have investigated adding. So what is the naive expansion? So when you have like a new element, just add a new level of leaves, and it will handle that. So we have investigated the new block size. What will be the new block size in that case? So we have some theorems, if you see, but it's better to see it as an example. If you have 2 to the power 30 elements, and you fix the overflow probability to 2 to the power minus 64, the leaf node should be 28 number of blocks, and the interior node should be 36. So, and basically in the naive solution, every time you are multiplying by 2 to the power 5, the number of elements, basically you should increase the leaf size by 1. So this is the rule. If you are, if you begin by an ORAM cloud storage, which is like 1 giga, and you are multiplying by 2 to the power 5, the number of elements that you have, you should add for the leaf node, the new leaf node, 1 block. So, but you can see that we are wasting a lot of memory. Just for 1 element, you should add basically you are multiplying the storage by 2. It's not good, because sometimes you are adding, deleting, you have this loop which is at the threshold, which doesn't make sense that you create the entire level for that. So it will not, the naive solution definitely is not the best solution, but we had to provide tightened bounds to see that this is the best that we can do with the naive solution. So what's the lazy expansion? The lazy expansion, it was like slightly presented by Gentry in their paper, when they say, okay, a level of tree in normal binary tree, you can store like the expected number of elements is 1, and you have a number of blocks which is log n. It doesn't have any sense. So they said that there is like a factor which is, a factor that you can divide the height to make this expected number of elements higher. So we are using, but taking into account also the communication complexity, because at the end we want to improve the storage overhead, but not at the point that we will decrease, make worse the communication complexity. So it should be also a trade-off between communication and storage. So the best factor that we have made is if you fix the number of blocks for your leaf nodes, so the blocks, the factor that you can divide the height. Just imagine that your height is log, it's n, you divide by alpha, it's log n over alpha. And delta is the security parameter here. So for example, for n to the power 30 elements and overflow probability to the minus 64, the interior node size is always the same, 36, but our leaf bucket is 85. It seems that it's huge compared to the one which is presented here, which is just 28, but making everything fit in the equation of communication complexity, we will see in our experiment that it's much better. We are saving 7% in communication complexity and 87% in storage. So just to give you an order, normally if you store 4 terabytes in ORAM like that, you should pay per month. If you take the pricing of Amazon S3, where a giga per month is 0.029, like 2 cents per month per giga, you should pay like around 8,000 for 4 terabytes. 8,000 if you store an ORAM, the entire ORAM. So with this optimization, you just pay 800, like 10 times less, 800 per month for 4 terabytes, which is huge. So which makes our technique, which makes sense, like 10 times less nearly it's a good save of money, of course. So
I'm just side note. If it costs just 800 a month, then it's like you can buy 5 hard drives locally.
I mean, the cloud is not just the storage, it's just the availability. You don't want your data to be lost, etc., etc. I agree, of course, but I mean, there are a lot of other factors for cloud. Yeah.
So the breadth intuition here is you're still saying I'm going to add an entire row at the bottom of my tree at once. You're just saying that then I'll wait until I...
Yeah, exactly, alpha times. Yeah. It's like a leaf, you can see it as in every leaf node can store alpha elements, the expected number of elements that it can store, where in the full binary tree it stores just 1. The expected number, because it's a binomial distribution, and the expected number of elements that you store in normal full binary tree is just 1. So what we are doing is a lazy expansion. We are waiting. Store alpha elements.
Is alpha greater than or less than 1?
No, it's greater than 1. It's like 15. It's around 15 or 16 elements. The expected number of elements per leaf is 16. It's around 16.
And by elements, you mean like that's the bucket size at the bottom? Is that the right word?
So it's like a block size. I mean, because in the tree you have these dummy elements as well, but you have 2 to the power 30 elements. So these are real elements that you are like taking your data set and dividing that in blocks. So this is what I mean by number of elements. So basically this alpha is around 15.
So how does this compare to if you started out knowing the pulse size and you allocated a tree for that size?
Yeah.
How does it compare?
The problem with this solution is, let's say that you have to know.
Just out of curiosity, how much do you lose because you don't know?
Yeah, I mean, if you have the same size, and you're using the naive solution, naive solution, you are not expanding. You have like initialized your ORAM and you are just putting elements on there. So it's like you are storing the maximum, right? It's like n leaves structure. It will be like what I have said, like 8,000 per month, if you are like storing these like 4 terabytes. So with this solution, if you are taking this lazy insertion, with the same block number of elements, exactly the same, with the same block size, you just pay for 800. Why? Because you have a height which is like very flat. The tree is flatter because you are dividing the number of elements by 15, n over 15, which is this alpha that we have here, and you create the full binary tree for that. At the same time, you are increasing, right? You are increasing the leaf bucket by 85, but it doesn't have that that impact on the storage.
So I mean, you shouldn't. I think that is my question. Right? So if you knew, like, if you just start up with this day with the new, with the larger database, suppose you like downloaded your entire ORAM database and you create a new one of the new size. How does the storage size of the new one compare to the storage size you get here? Presumably it would be a little bit smaller.
It depends. If we are in the scenario where you are adding, right?
Yeah, so suppose instead of changing the numbers, like just adding another row, I want to add an element to my database, I'm going to download my entire database and do it, like generate a new ORAM.
Okay.
So like the optimal.
The problem of this binary tree is when you have n elements, let's say you have n elements, you can create a full binary tree of n, okay? So if we take the solution which is not dynamic, just add a new leaf when you have n plus 1. Just imagine you have n plus 1 elements, so you should add a new set of leaves, like to have 2n instead. And 2n is huge for n plus 1, right? But this is the naive solution that you are, right? This is what you are thinking. Or you are thinking about the dynamic, where you are just 2 leaves. 1 leaf. This is what I will talk about.
I think the question is how much overhead is there?
The overhead, just imagine if you are downloading the entire ORAM. So you have 2n-1 node. Every node is log n. So it's huge to download and modify and then upload. Even if you are thinking like that. So if you think about what's technique you are using to increase the ORAM, if you are just thinking of it like increasing the level by adding a new level of leaves, which is the naive, of course, solution, it's not good. Even if you are not downloading and just adding, saying to the cloud, okay, create for me a new level of trees. I will percolate towards them. So it will not be also good.
Can you also create like just one extra?
Yeah, exactly. This is the dynamic solution, but it has some problems actually in terms of overflow probability that I will explain. But the naive solution, it's the worst compared to all this lazy or dynamic. It's the worst.
So what if I'm doubling the size of my database?
Okay.
So
Exactly. True. No, this is
Just in this case.
We will see in the experimental part the graphs that they are like stairs, and at some points, as you have said, if you have exactly doubling at the same time, from n to 2n, it's like the best scenario with the naive solution.
Right.
Yeah.
You can add a new layer.
Yeah, exactly. You can add a new layer, and it has like less repercussion on the difference between lazy and naive. You will see that it's different.
So does the lazy, say the storage and the lazy solution end up being worse?
No, it's always better. It's always better. It's always better. It's always better because you are flattening your tree. But as you have said, in these points, when you have n, 2n, 4n, you are doubling by 2, it's the best case. Because you are not wasting the storage that much. You are not creating like an empty leaves. You are creating like normal ORAM, like a normal ORAM in that case. But when you are adding like one element, if you are thinking in naive way down on the entire and create a new ORAM, it's huge amount of data. You cannot do that. If you are just going with the solution that you add a new set of leaves, this one will be also bad because you have just one element and you are creating the entire level of trees. And if you are just doubling, this is good. This is the best case for the naive solution. For the lazy, it will be also alpha n. This is the best because you are not losing also size, the storage. Because here the problem of the lazy solution, when you have a level, let's say it handles alpha n, and when you have alpha plus 1n, also you should create a new set of leaves as well. And it's a waste of storage as well. So this is the problem. This is why the dynamic solution might be better. But the dynamic solution, it has like a problem of the overflow to stay oblivious. The proofs show, you have to have larger block sizes. Instead of 86, 85, you should have 130. So I think that I didn't put it here, but it's 130 nodes. Just imagine that instead of 85, you have 130 nodes. So we will see in the graph the behavior. So actually this one is the communication complexity when you are downloading like an element. Of course, we want to save in storage, but also to save in communicate. We don't want to make the communication worse. At the same time, we want to give like the best storage that you can have. So in communication, we are better than the naive. You can see the stairs that I have told you sometimes. You are getting the same communication complexity for larger number of elements. And here the dynamic, you see that the difference is like the worst when you are using a dynamic solution. So this is why I'm telling you this difference is like the shortest compared to all other phases when you are adding like n plus 1, n plus 2, n plus 3. When you are adding by 2 times, it's like the best. And so this is the dynamic, it's like linearly increasing. And also the lazy increase, as I have said, it has like the same problem as naive solution, but you should wait alpha times more. But you can see that it's better. In terms of number of blocks you are downloading. In storage, it's huge. In storage, you can see the difference. With the naive solution, it's bad. So this one is logarithmically, and this one is not. I think that it's linear. So the number of blocks. So you can see that normally it's 89% of difference between a naive and lazy and dynamic solution. So the dynamic solution, sometimes is better than the lazy solution, sometimes is good, because it depends on the overflow probability. When you have, just imagine picture that's a tree. It has like number of leaves in the left, and it still has number of leaves in the higher level. So we still keep an overflow probability which has like the same indistinguishability property, which means that when you are inserting a ball, which is like an element in the ORAM, with the same probability it will go to all leaves, which means that for the leaves which are in the deepest level, it should increase by 1. Why the highest level it should be 1. So you when you are adding eta, let's say eta elements, at some point you should study your function that should take the maximum. And this is why we have this this intersection point between this phase and this phase. So when you are adding like 1, 2, 3, 4 elements between these intervals, sometimes the dynamic solution is not much better, but it's better. In general, it's very hard to say who is the winner between these techniques. But in general, they are much better than the naive solutions, which is like just adding leaves and making the ORAM works. So let's talk about this. These are just adding. So pruning is a little bit tricky. As I have said, it's not straightforward to say, OK, I will delete an element, delete 2 nodes. I have like 1 element less, I will delete 1 node. I mean 1 element and something like that. Because you don't know what is the number of elements that you have in your bucket. The straightforward solution is just read this bucket, see how many number of elements, and evict the number of times which is equal to the number of elements. The server will know the number of elements in that case, which is not good. So the other solution, which is using an oblivious sorting algorithm. Just take all your tree. For example, you have 3 nodes, for example, here, and you want to merge them obliviously. Just take the buckets, okay, and make them look like 1 bucket and use an oblivious sorting on them. And let's say that you are using a block which is like coded on FF, which is like always the largest block. It will be always at the end, and you just pick the first bucket, like log n buckets, and you say that this is the merged bucket. The problem of this algorithm, for example, one of the best is oblivious shell sorting, which is if you have n elements in your buckets, in your array, you will do the oblivious sorting in n log n. Okay? So we want to do something better than that. So what we thought about is, this is the first solution that I have described. We don't have n, we have log delta elements per bucket, so we have log delta, log delta. But the solution that we came out with is, imagine that you have 2 buckets, like child 1, child 2. And we add a header to every bucket. So this header actually will show on which place the element exists. Let's say that it's just an array of bits, and 0 if the element is not there, and 1 if the element is there. So these headers are log. If we have log delta block, it will be log delta bits. Okay? If it's log delta bits, it's like it's a O of 1. It's constant block, because the block is log delta. So the client will download both headers, okay, right? And we create what we call an oblivious permutation. So we take the first header, we know on which place there is the real element, and we randomize it. It's not necessarily, but just imagine we randomize this position, the permutation. We send to the server, okay, take this element here, take this element here, and you randomize the blocks there. The second permutation will make sure that when there is a real element, it will permute it to a place when you add both blocks. They will not overflow to each other. It will not be, we will not have a block in the same position. For example, we have element 1 here, element 4 here. When we are adding using, for example, partial additive homomorphic encryption or something like that, when you are adding, it will not work. So we make sure that when we are permuting to the place where they are empty. So what's the cost of this permutation? So the permutation is, if you want to permute an element to another place, it's log delta, and to another place. If you want to send the permutation at once, it will be log delta, which is the same as the oblivious sorting. So what we thought about, which is a little bit a small trick, so the server will keep the header here, he will know which position actually is full. And it will permute, after permuting this first one, it will permute just by sending a query at once. Give that this here, change this position here, and it will be at every time log delta. So our purpose in this permutation is to make sure that at any time, the server will not store more than log delta, which is a block. It's okay if it stores log delta, I mean twice or something like that. But we don't want to send, because the client cannot put in his memory log delta, which is like more than one block, and it will not be constant. So we should send like in several times the positions of these permutations. After permuting, so there are actually two solutions. The first one is like partial, we merge with additive homomorphic encryption, but it needs a computation of the server. This is what we don't want to have with Amazon. It's not a computational server, it's just a storage server. And we want to take advantage of that as well. Once the server can, for example, permute the positions, we can always create an empty bucket and download first, second, and push. Download first and second block and insert in the third bucket. And also in constant client memory, we can do that. So we will have our results in bucket. So this technique is working only for 2 buckets, but you can understand that you can take these 2 buckets and add the parents and merge everything. So at the end, we will, yeah.
So the headers there, that's encrypted on the server.
Yeah, it's encrypted, yeah, exactly. Because otherwise, the server will know the positions and it's there.
Right. So what you're saying is that you can sort of generate this permutation.
Yeah, based on these bits. If you have 1, it means that at that position, let's imagine that this header like is 0, 0, 1, 0, for example. It will know that at the third position, when in the bucket, there is like an element. For example, here 0, 1, 0, 0, 1, 0, 0. And you encrypt that in the header.
And so the first solution was you download both these headers, you figure out what the appropriate
Yeah.
permutations are, you send them back.
Exactly.
To the server does them.
Yeah, exactly. Yeah.
What was the second solution?
The second, this, if you think about it like that, what is the size of the permutation? If you have log delta, you should have log delta time log delta, so which is not constant in the block size. So what you can do is just permute the first one, okay? And you keep in memory of the client this header, which is like log delta bits, which is 1 block. So you know what's the other permutation you will send to. For example, this element, you will send it to the first, the second element, and it will be just log delta communication each time. No, instead, just picture it like instead of sending at once, you will divide atomically the permutation that you will send. So this is the trick. Just because we should make sure that it's always constant client. Otherwise, it will be, different than constant client. At the end, we merge either with additive homomorphic encryption or just by the trick that you download both positions and you put in the third bucket, empty bucket. It's the same, but with different technique. So to conclude, actually, so what we have seen today is a technique to enhance the search communication complexity of tree-based ORAM from one hand. The second hand, we are tackling a new aspect of tree-based ORAM is how to make it resizable, how to resize it and make it, friendly, cloud friendly. Just to make sure that we can really apply Oblivious RAM to a cloud scenario. We should tackle this small aspect that sometimes we forgot about it. So we have still a lot to do. We still have to improve the communication complexity. You still see that in our graphs, it's still large. We have a log, in asymptotically speaking, we have log multiplicative factor, log n. And it's not good. If for normal clients, some of them, they are not ready to pay log n times more, like 30 times if you have 2 to the power 30 elements or something like that. They are not ready to pay that. Also in communication or in storage. So we didn't study the resizability of polylog ORAMs. This will be maybe in our next work. And the last question that we are asking ourselves and we are investigating, is tree-based ORAM the best way to model the ORAM? Is there anything that we can model the Oblivious RAM in a better way? Because now the idea of the Oblivious RAM community now, they are just taking tree-based ORAM and optimizing the eviction, optimizing, for example, the hide, they are optimizing everything just to make this small factors. But we are asking ourselves, is there any other way, maybe, to model the ORAM in such a way that we gain? Because we should get out of this ball and think outside of it. So to think how we can optimize better in better than logarithmic in the number of elements. Thank you to be here.
Yeah, we asked a lot of questions and we're running a little over, so maybe just any other questions? Feel free to go ahead, Kath.